Hey everybody, in this bonus video, I'll be going over a somewhat simple implementation of gravity on the GBA. So I imagine a lot of you guys are going to be getting some mileage out of this if you plan on making a side-scrolling platformer for your final project. Because without a system for gravity, what you're basically going to have to do for a jump is your player is, for instance, maybe on the ground. In order to make the jump, you're going to have to make their velocity negative and make them go up, hit some point in the air, then instantly make their velocity positive and make them come back down to the ground, basically. So this is kind of awkward because in real life, when you jump, you don't really like just translate up at a set velocity, hit a point, and then instantly come back down. Like that's kind of weird to think about, right? Like imagine somebody do that in real life. What happens in real life is you're standing on the ground and you decide to jump. So there's this big push, and you have some upward velocity at the very start of it. But as you go up, that velocity sort of decreases in uh, in magnitude, I guess, until you reach the apex of your jump, which happens when your velocity hits zero because it's decelerating, and then you start going back down. Velocity picks up in the other direction, and you end up back on the ground once you've fallen far enough. So, this concept of acceleration is what makes a jump feel like a jump. You're accelerating downwards this whole time, not necessarily switching up your velocity manually. Um, the difficulty on the GBA, though, is that it can be hard to get these values to look natural without sort of being like very big numbers. Like if we were to take this number, start at 5, then instantly go to like 4, then 3, then 2, then 1. There's a really big difference between the speed at like 1 and the speed at 5. And like to give like some context to that, the screen is 160 pixels tall, right? You divide that by 5, which is like the number of pixels you'd be translating every frame if you're moving at a velocity of 5, you would end up moving all the way down the screen in 32 frames. That's a little bit over half a second to traverse the entire screen. That is extremely fast. So we want these numbers to be interpolated at like both a natural rate, but also in a way where it's like not happening too quickly. And a tool that we have at our disposal in order to make these numbers interpolate that we want them to is fixed point encoding. I know it's scary. You guys probably haven't used it in any other projects, but it makes gravity feel really good. So it's worth discussing here. So in the demo code we're going to be working with today, the values that we're going to be working with for y and dy are going to be encoded in 8.8 fixed point encoding. Basically, all that is say when these are 16-bit values, right? Eight of those, eight of those, um, eight of those bits are going to be to the left of the decimal point. Those are the ones we're going to actually be looking at when we actually like draw stuff or read these values. And then we're going to have eight bits on the right side of the decimal point, which are going to be hidden values that we use for internal calculations, maybe like between y and dy, because they're both going to be encoded. But if we ever want to, for example, like compare y with like the player height or something like that, we'd want to decode it first. So we're talking about encoding and decoding values. Let's say we want a y value of 20 and maybe a dy value of 1. If you were to add these two values together, like if you were trying to move y by dy or something, you expect this value to end up being 21 because y plus dy is, well, it's 20 plus 1, which is 21. So When we encode our values, we want to do something like this. We want to shift them left by 8, right? So if we do this addition between the two of them, then we would actually get 21 bits shifted left by 8, and our math would stay consistent basically. But if we were to add like a value that wasn't encoded, we'd get some weird decimal there, basically. So if we ever want to decode these values, what we do is we just take the value that we have, y, for example, and we bit shift that right by 8 places. And that's going to bring that 20 or 21 that was originally bit shift left by 8, and it's going to bring it back to being just a regular 21. Because we are going to need those regular values back if we ever want to draw our stuff to the screen, for example, because 20 bit shift left by 8, that is not a y value that exists on our screen. That is very far beyond the y values that exist on our screen. 20, on the other hand, that does exist on our screen. We can use that. So we can bit shift it back to the right by 8 to get those values we actually need. So with that preliminary stuff out of the way, let's get into some programming. There we go. So let's get the lay of the land a little bit. We got two files we're going to be looking at today. We've got demo.h, which is going to have some useful stuff in it. We've got, first of all, a couple things to do with gravity. Of course, we have gravity. This one's set to a value of 80. Seems pretty big if we're talking about an acceleration value, but due to the fact that we're in 8.8 fixed point encoding, this is actually quite small. This is going to determine how fast our objects accelerate downwards, basically. Terminal velocity, if you're familiar with the concept in real life, if you were to be like skydiving or something and you were falling, eventually you would hit a sort of max speed due to like the confliction between gravity and air resistance. And this value right here is basically saying, I want to cap off my possible downwards velocity at this point. And in this case, it's 1300. That is also going to be something that's shifted up by 8, or at least like used with encoded values, so its value is fairly high. Got shift up and shift down. These are just some nice macros we have to actually do our bit shifting. Shifting up is for encoding. Shifting down is for decoding. Got some quality of life things here with these macros. This is a clamp function right here. Basically what it does is if you have a value, it'll return that value back to you unless it is outside of a range you've defined with this minimum and maximum argument. If it's below your minimum, it'll return the minimum. If it's above your maximum, it'll return the maximum, basically. Floor and ceiling are essentially this, but one-sided. Floor makes sure your value is above a specific value, which is your floor, and ceiling makes sure your value is below a certain value, which would be your ceiling. Also got this hitbox struct here. That's basically just a rectangle. We've got our x, y, width, and height. And we've got a player struct, which is going to be the main thing we're looking at today. Of course, we've got x, y, width, height, dx and dy, and we have a couple extra things as well. We have this grounded variable, which is essentially going to be a Boolean for us. It's going to tell us whether or not the player is currently grounded. We have this jump count variable here. We're going to use that a little later on when we're messing with jumps. We've got jump force, which is going to be the initial velocity of our jump. This is going to be another really big number like these ones because we're going to use it to mess with our encoded values. And in main.c, we got some initialization going on. We're in mode 4. We've got some stuff for our player struct. We've got some stuff for our ground struct. Have some X movement stuff here. Got some empty space here for our Y movement, which is going to be where we implement gravity. Ooh, spoilers. We've got a draw function where we are going to be drawing the player, and we've got our main loop down here, just the standard mode 4 stuff. So what we're going to see when we first open this is we're going to see a white screen with a red rectangle floating in midair with a little bit of ground underneath us. And in our next step, after we take a look at this, we are going to make that rectangle fall. So here it is. This is going to be our player. And our goal here is going, at the very first, is going to be to make this fall to the ground. So let's get started with that. First off, we have these two values here we want to encode, y and dy. So first thing we want to do is we want to go ahead and encode them when we initialize them. So we can use the shift up macro to do that. It's going to shift up 20 by 8 bits, 8 bits to the left. We can also do the same for dy. In this case, it doesn't necessarily matter because we are working with a value of 0 for its initialization, but just to be thorough, we might as well do it. And a place we're actually using player.y right now is in draw. It's going to be red here. And if we leave this the way it is, it's going to try and draw our rectangle at player.y, what its raw value is, 20 bits to the 8. We don't want that, so we can shift it down here, and that will allow us to get the real value that we want. So that's the first thing we want to do. Let's also set up some of the initial variables here that we had for player that aren't here right now. Let's set player.grounded to 0. Maybe we want to start our player airborne and do that check and update whenever we hit the ground first. Let's also set our jump count to 0 for the same reason. Eventually, we'll be setting it to higher numbers that allow us to jump. Who would have guessed? And lastly, we have jump force. Since this is going to be an encoded value, we're going to make something high. Let's make it 1300. Also make sure this is negative, because, of course, in the GBA, all the low values of y are going to be higher than the high values for y, as counterintuitive as that is. So we want to make our jump force negative to make us go up. So that's initialization out of the way. So let's actually make our player fall. The first thing we want to do here is we want to figure out what the y value is just underneath the player. And the reason we want to do this is because if I scroll down here a second, show this. We need a way to know whether or not the player is touching the ground. And a pretty simple way to do that is to look at the area just underneath the player, just 1 pixel's worth of space here, and say, okay, is this rectangle colliding with this rectangle? In this case, they are, so they're grounded. If you were like 1 pixel upwards, then this rectangle would be right up against the ground, but it wouldn't be actually like going into it and touching it. So it wouldn't be colliding and you wouldn't be grounded. You'd keep falling. There is also a possibility that you sink a little into the ground when you do this, because this also counts as a collision, right? They're overlapping. So this is a possibility. We will fix this in a bit once we have got this all set up and running. But yeah, we're getting ahead of ourselves. Let's just go ahead and just find that value. So let's call this bottom y. And this is just going to be the normal thing, player.y plus player.height. That should get us the pixel below the player. However, again, player.y is encoded, so we need to decode this before we have it interact with player.height, because player.height is not encoded. So we can shift this down, and this should give us the actual correct y value that we want for bottom y. So let's also do the logic here for taking off the player's grounded. We discussed it was a collision. So let's set that up. Player.grounded. That's going to be set equal to a collision function. And that's going to be a collision between the ground and that area right below the player. So for the player, we would do player dot x for x value, player dot y for our y value, player dot width. Oh, I messed up. This should not be player dot y. This should be bottom y. That's why we just calculated this. So player dot x, bottom y, player dot width, and we're only checking one pixel below us, so we just want a height of 1. And for the ground, we've got a nice struct for that. We can just do ground.x, ground.y, ground.width, and ground.height. Just like that. So that's going to tell us whether or not the player is grounded. So we've got this big if-else statement here. We're going to put a bunch of stuff in here, but for now, let's just set the player's velocity to 0 when we're grounded. Player.dy equals 0. Just like that. And in the else statement, we want to make sure that we're accelerating downwards if we're in the air. So in this case, we might want to do something like this. Player.dy is equal to player.dy plus gravity. So let's see how that looks. Actually, before we see how that looks, we should probably update the player's y position based on its y velocity. Looks like it's already building. We'll just type while it's happening. Player.y plus equals player.dy. That'll actually make the player's position update. You can see it's not moving right now. We want the player's position to actually update with the velocity value that we've given it. So we definitely want this line here. This is very important. So maybe this will run eventually. And we should see the block falling here. Yeah, set that down. You can kind of tell that it's speeding up a little bit as it falls. It doesn't look particularly like static, I guess. It's bouncy, it's lively. This is good. This is the direction we want to go. But you can see down here, we are poking a little bit into the ground after we fall. So we do want to get rid of that behavior because obviously we don't want our player to be in the ground. We want them to be on top of the ground. So let's think a little bit more about the situation. So let's say I've got a block and it's above the ground. Let's say it's 3 pixels above the ground. But our block is falling at a rate of 5 pixels, just like that. Basically what's going to happen here, if we leave it alone, it's going to move 5 pixels on the next frame, and it's going to end up around here, 2 pixels deep into the ground. We don't necessarily want that. So what we can do to avoid this is we can define an area under the rectangle, similarly to how we've done with grounded, except instead of doing a height of 1, we do a height of our speed, 5 pixels. So this would go into the ground some ways, pretend that line is straight. And as you can see, if this is the ground here, and we check for a collision between these two blocks, then there's a collision right here. These are overlapping. So in this case, what we would want to do, because these two are overlapping, is we would want to take this velocity and set it to what our current distance is from the ground. Take it from 5 pixels per frame to 3 pixels per frame. And that mostly fixes our issue, right? However, there are some times where this can go wrong and you still end up a pixel on the ground. And the reason for that is because just how decimals work, right? in how rounding works. Because say you have a value of like 4.5 for this. Actually, I'll use 5.5 because this is 5 here. A value of like 5.5 for your velocity, and maybe your y value behind the scenes is like, I don't know, 160.5. If you add these two numbers together, of course, you're going to get 167 because that's what these two numbers added together are. Oh, wait, no. I'm a fool. It's 166. Yeah, it's 166. And that's what you'd expect to get, right? However, if you were to shift these numbers down if you were to shift them up and down, what would happen here is these numbers actually get truncated, right? Because when you're shifting an 8.8 number back by 8, these bits get removed from your number and you just end up with the 8. So just by doing a little bit of rounding, you get rid of these and end up with something like 165, which isn't what we want. So when we're doing this collision check with the height, we just want to make sure we're adding one extra to this. So this block would have a height of 6. So that's 1 plus your velocity. And if you have a collision between that box and the ground, then you want to set your velocity to this 3 here, or whatever your distance actually is in your project. So let's go ahead and write some code for that. First thing we're going to do, we're going to make a variable called ground check. This is going to be a Boolean for us. It's going to determine whether or not this collision actually occurs. So another collision is going to happen here. And the first thing we're going to have is we're going to do player X again. We're going to do bottom Y again. That's going to be the top left corner of our collision box. We're going to have the player's width. And for the Y, what we're going to do here is we're going to do player.dy plus 1. And the plus 1's there just to account for the floating point error. However, again, 1 is not a fixed point encoded value. So we want to shift down with player.dy by itself, and then add 1 to that value, just to make sure the math lines up. And once again, for the ground check, we can just do ground.x, ground.y, ground.width, and ground.height. And this should keep us from, oh, well, if I were to actually have the velocity match, that would actually work out for us. But this all is right here. You can see it's still in the ground. We haven't read that code yet. I have a habit of building my code before it's actually ready, so that's my fault. We'll try and stop that. Okay, so let's actually make this collision check do something for us. So if this condition is true, this ground check happens. We want to reset the value of player.dy to the distance between the ground and the bottom of our player, which is just ground.y minus bottom y. Just like that. And now we've got an interesting case. Player.dy is our encoded value. These right here, that's a minus sign, these right here are not encoded values. So in order to make this thing work the way it's supposed to, we need to take these non-encoded values and shift them up because we are writing to player.dy here. And that right there should just about do it. Now we should see it where the block slows down just as it hits the ground. It'll be imperceptible, but it'll happen, and it will not fall through the floor. There we go. There's no more overlap between these two blocks, and that's what we like to see. So before I go on, I want to address something that this video isn't going to necessarily do in code, but I still want to do the idea justice. We have not covered collision maps yet, but we will get there fairly soon. And if you are planning on using a collision map in your project, this process right here of figuring out what pixels are in this area, or like necessarily what's colliding with what, is going to be pretty different because collision maps work in essentially where every individual pixel can be checked whether or not it's a collidable object, basically. So instead of doing like a big collision box rectangle down here to determine if you hit the ground, what you generally have to do is figure out what this top left corner is for this box, and you know the width and the height of this thing. You just run a for loop through it if you want to be really thorough, and check all the pixels to make sure if any of them are actually like collidable, basically. That's what you would want to do. If in many cases it actually works out where you just need to do this column here and this column here, and that usually works fine. But if your collision map's a little more detailed and has like really thin platforms, you might want to do the whole thing just to be sure. But yeah, it's a different process with collision maps to do this specific step, but the rest of the algorithm is going to be the same. I did want to point that out because a lot of people are going to be using collision maps in their final projects, and yeah, it's very useful to know how that would work. We're just not going to do that right now. That is a later topic. So things are looking pretty good so far. We can make a couple adjustments. One thing here, if we were to allow the player to fall, it like forever without touching the ground, they would just accelerate forever and never stop. So one thing we can do to make that not happen is we can cap out this value at our terminal velocity. What we can do here, we can just use our ceiling macro that we defined from before and make that maximum possible value for the downwards velocity, terminal velocity. Basically, if player.dy plus gravity ever goes above terminal velocity, this will just set it to terminal velocity, and then it'll never accelerate past that point. That's one thing we could do. Another thing we can do here, you might run into a weird edge case, especially if you're with collision maps, where maybe you have a ledge and you're jumping right up against the ledge, and you're checking this area below you to see if you're grounded. And you might round the corner or something like that, and end up in a spot like this, where you're just barely hitting this corner on the collision area, and this would register as true, and it would stop your movement upwards. So you would kind of get caught there. So one thing we can do to avoid that is when we're grounded, rather than just straight up setting our velocity to 0, we can do make this a maximum for our velocity at this point, because if it goes higher than 0, we start falling. So, but if we are below that, then we could just keep going upwards. So we can do another ceiling function here, where we just basically have player.dy right here. And just, it basically says, keep dy the same unless it's 0 or greater than 0, in which case, just set it to 0. And that would avoid something like that happening, which could be nice. Pretty niche, but it could work out for us. So this is cool and all. We've got a player falling, but it's not necessarily all that fun just to the player fall. The real fun of it comes from jumping, being able to jump around. That's the fun part. So right down here, we've got this got this code here we're going to write in to actually make the player jump. And the idea here is we're falling at some speed at this point, right? If we press the jump button, we want to completely overwrite what this velocity value is before we actually have the player move. And want to overwrite it if the jump conditions become true to whatever our jump force is. So first of all, let's give ourselves a condition to allow us to jump. Pretty simple one that works in most games. Just check if the player is grounded or not. If the player is grounded, then you can jump. And if the player is not grounded, then you can't. And that could affect this condition right here, which allow us to whether or not we can jump. So yeah, in order to actually make this thing jump, what we just have to do is we set our player's dy, or velocity, to what our jump force is. And that's pretty much all you need to do in this step, pretty much. And if we allow that to happen, if this happens, then player y is going to move upwards by this value. So let's go ahead and try this out. It's building. Yeah, so it can move around a bit along the ground. But if we press the A button, get a little jump. Look how great that looks. That's awesome, right? You can just move your guy around and you can make him jump. And it actually looks like a jump instead of just going up and going down. So cool, right? Who's making a platformer? Pretty some platformers this year. Yeah, that's a pretty basic system we've got going on. But what if we want to do something cool with jumps? Maybe we want to have like a double jump, a mid-air jump. Something we can do here. And I want to emphasize, this is not the only way you have to like tell the player whether they'll make the jump. There's plenty of ways you can go about it. It really just depends on the kind of game you're making. So if we were to go and do something like this, we're basically saying here, okay, I'm storing some number of jumps on my character. If that jump count exceeds 0, if I have a jump, I can use it. And if I don't have any jumps, I can't. This is valid if you want to have something like a mid-air jump. So maybe if we're in the jump function and we want to like lose a jump whenever we use one, do something like this: player dot jump count, just like that. And maybe we reset that player's jumps when they hit the ground. Something like this: player dot jump count equals 2. Now what's going to happen, instead of waiting until the players hit the ground to allow them to jump, if we hit the ground, we get 2 jumps. And the moment we leave the ground, that value is no longer being set to 2 every frame. So it really just depends on when we use these jumps. Like in here, we're subtracting from our jump count every time we press the A button, and this is true. So if jump count is 2 and we jump, we go airborne, our jump count becomes 1, and this condition is still true, so we can actually do this again. If we do it again, player jump count becomes 0, and now this condition is false and we can't jump anymore. So we run through this, we should be able to see a double jump. We should be able to do it. If you spam the button in midair, you should only be able to get up to 2. That's pretty changeable. But I'm just showing you here, there's more freedom to the way you can get this done. Like I'm spamming the button right now and I can't get any higher than this. But I can do stuff like this, which is pretty fun. And also, with the gravity and terminal velocity stuff, you can kind of change the physics of how things work. Like, if I make this value like, I don't know, 40, something like that, probably want to decrease the jump force on this just to be, well, safe. Because if we're decelerating, or I guess if we're accelerating downwards at a slower rate, then these higher values in the jump force would be present for longer, and you'd go sky high. But you can sort of mess with these values like this and get different feeling jumps. Like this one here. If I jump, it's a little floatier. Kind of low though. Let's make the jump force a little higher. See what happens. Let's make it 1200. See if we can get a kind of moon jump going. Yeah, we're falling really fast. Look how floaty that jump is. That's kind of awesome, right? It's like you're on the moon. Oh, we went off the screen. That's cool. Don't worry about that. It didn't happen. Yeah. So that's basically gravity. Um, if you're doing platformers or any game that requires this type of movement, this is an awesome way to implement it. Um, all sorts of different vibes you could go for. You could go for like super heavy jumps with like high gravity and a decently high jump force where you jump decently high but you fall really fast so you feel heavy. Do the exact opposite we've got going on here. You've got a space game. Want to jump around on something with really low gravity. A lot of cool stuff you can do with this, guys. A lot of cool stuff. So yeah, that's pretty much all I've got for you today. So I will I will cut it off here, and I wish you guys luck with your final projects.